Welcome everyone, my name is Robert JAROSZ. I am a PhD student from Military University of Technology in Warsaw. Today I would like to present multi-agent simulation and reinforcement learning library that I am currently developing. The library name is Amphitheatre and it is being written in Rust, and it is published under MIT license. Firstly, I would like to talk about requirements I'm willing to meet with this library. The first demand for libraries is to make it efficient and gently scaling as simulated model gets more complicated or involve rising number of agents. Also, the library is expected to support construction of models distributed over the network in the way that transferring medium is transparent for sides of simulation. Nextly, reinforcement learning support. Toolsets should provide convenient tools for generating and collecting learning data during subsequent simulation and possibly some generic implementations of known learning algorithms. Finally, compiler-level model correctness. It would be good if model could be compiled and during the process the researcher or programmer is aided with language tools to ensure correctness at some level. At the beginning, I have said that library is developed in Rust language, and here I will briefly discuss why such decision has been made. Firstly, Rust provides type safety during compilation, ensures that during program run, the structures and objects have types that are compatible with requested interface. Secondly, Rust is memory safe. It ensures that there is no possibility of accessing dropped memory area or memory address outside of bound. Rust has this innovative memory ownership model that achieves memory safety without sacrificing performance for using garbage collector. Thirdly, Rust has fearless concurrency model, guaranteeing that data races and uncontrolled access to shared memory do not occur. And ownership property is enforced across all the threads. Next, Rust is fast. It's really fast. In performance, it is often compared to C++. It is used to build system measures and drivers. And finally, the Rust compiler is really helpful. Errors are diagnosed and often clearly explained. And even sometimes the solution is to fix the problem is suggested. Now I will talk about a problem that library tries to address. The said problem is multi-agent reinforcement learning. And as the name suggests, it is reinforcement learning problem with extension of many agents. Traditional single-agent reinforcement learning is a technique of upgrading algorithms' accuracy in solving problem. Agent is dropped against environment which represents some problem to solve, typically a game. Agent performs actions and observes change of state and is fed with reward. Agent collects experience over repeated experiment and apply it to update his policy. Typically, agent performs one action and observes change in the reward, then takes another action and so on until the end of the simulation. The multi-agent problem expansion brings several more things to consider. 1. What is the order of players, whether they act simultaneously or in some specified order? 2. How to define observation and reward if state of game change several times between two subsequent actions of one player. It may be done by actions of other players that change the state of game. 3. What can be run in parallel and how to avoid data races. The proposed library uses concept of running agent and environment in separate threads. Agents communicate with environment with bidirectional queue-like channels. The channel implementation may use different underlying mechanisms, such as Rust standard library, multiple producer, single consumer channel, or some network protocol like direct TCP level stream or some HTTP requests. These mediums should be transparent for agent and environment implementation. What is more, each agent must have possibility to implement his own view on the game state. In game theory, called as information set. Some agent may store raw observation, some agent may try to filter some interesting information and drop that they mark as irrelevant. Sometimes agents base their action on the last observation, sometimes they construct the information sets to include observation history. Finally, different agents may represent different type entities with different roles in the model. So to provide medium transparent communication model and some freedom of entity implementation, a game domain is to be defined. The structure describes types that represent update or observation, action, reward, and error type to announce some problems with model. These are the types that all entities must agree upon in order to build functioning model. From the agent or environment point of view, they send in-memory structs or objects into the channel, and it is channel role to deliver it to the recipient in correct order. It may be in-memory transfer, inter-thread communication on local machine, or packed for network transfer and pass it on the other side, all without bothering environment or agent logic. When agent has game parameters agreed on, he can implement his logic to interpret incoming environment messages and produce valid agent messages. In fact, a generic implementation of automatic agent performing simple protocol is already implemented. This implementation requires, however, defining of some traits on its information set and policy. Namely, information set transition upon receiving update, and producing action with agent policy over information set. With properly defined information set logic and policy, agent can work autonomously. Other agent of game can use different type of policy and different information set. Similarly, the environment controlling the game has generic automatic implementation that requires only proper logic implemented on underlying template type of game state. This logic is basically transition of game state with player action and production of update structures for agent. Optionally, and typically it is so, game state may calculate actual payoffs of agents that will be used by automatic implementation to produce and send rewards to them. And here I will discuss approach to problem of multiple rewards and observation per single action of agent. The problem may occur in sequential games where agent can observe several changes before he can act again. Amphitheater model support issuing observation and reward once, just before this agent next action, or as partial update on the game state as seen on the feature. The first approach seems intuitive and easier to handle by agent. He works just like single agent problem. However, it may bring complication in implementing game state on environment side, as now environment must track what to update for every player. This model may be seen in Petting Zoo library developed by Farama Foundation. It's current community standard for multi-agent reinforcement learning. Second approach is issuing an update to all interested agents when it is convenient for environment. Then, agent must implement a way to deal with multiple updates. Investigating game flow shown on figure, Agent 1 observes direct consequences of his own actions, and later observes consequences of actions of Agent 2. Agent 2 action could produce observable consequences for Agent 1, as well as change his payoff. Therefore, a correcting reward message is sent to Agent 1. This approach needs ability to send messages by entities at any time, and since Amphitheater library bases on synchronized threads, it was adapted here. The second way is compatible with the first, as game state can be implemented to output update only for player that is next to take action. Previously, I have mentioned Petting Zoo, a Python library developed for multi-agent reinforcement learning problems. This library is designed to provide similar API to popular single-agent library of Gymnasium, also developed by Farama Foundation. The primary concept difference is that Petting Zoo standardizes programmer interface for environment, leaving agent implementation for researcher, and Amphitheater standardizes protocol for the game, provides environment and agent following protocol, provided that the game state, information sets, and policies are implemented in compatibility for game domain. Automatic agent implementation also comes with trace collection, relieving models from this procedure. Current slide provides comparison of top-level model codes of petting zoo, AEC, Automated Environment Cycle environment, and amphitheater invocations. In petting zoo, programmer selects agent in loop, gain his update and reward for previous action, and select new action. In amphitheater, on the other hand, all entities run in dedicated thread, communicating with defined protocol. Compare computation performance of models written with petting zoo and amphitheater, I have conducted a simple benchmark. In this benchmark, I compared execution times of models written in Python using petting zoo, model wrapping Python zoo environment in amphitheater game state, and pure Rust implementation of environment. Models use the same neural network backend library, which is libtorch, and equivalent implementation of advantage actor critic policy. We can see pure Rust models execute at least 3 times faster than Python. Wrapped models' performance lies somewhere between, and we can see that with neural network layer size of 10,000, Python model already suffers with visible performance downgrade, probably due to host computer limitation exposed, for example, by large number of involuntary context switch observed on processor. Similar experiment has been performed with network built with 2 hidden layers. Once again, Rust model was visibly faster, although more benchmarks are to be done involving different host capabilities on different problems. The current measurements are promising. For models that are expected to learn for days or months, even halving execution time may be worth effort using Rust. Another benchmark I have made is dedicated to communication mediums used for models. For experiment, I have built a model of multiplayer variant of multi-armed bandit problem. It has been chosen due to a small amount of state processing, so relatively more work is done for communication. Without surprise, local communication is faster, actually several times faster. However, for larger number of players, rational difference is getting smaller. What is worth to note that the performance scaling is worse than linear. Currently, environment checks for messages in channel in round-robin manner. Future implementation may use another thread for dispatching incoming messages, what might improve scaling. It is yet to be done and tested. The library needs more work to be fully usable by community. Future work includes API documentation and stabilization, improving communication performance and delivering different mediums for network communication. And last but not least, adding more generic implementations of reinforcement learning algorithms. To conclude my presentation, I would like to say that the library has its demonstration possibilities, draft documentation, and several examples. It is on early stage of development though. API will likely change and lacking features will be delivered. So be warned. And nevertheless, I invite you to take a look at documentation and code someday. Suggestions for improvement are always welcome. And thank you for your attention.